A black hole the size of a city, and another so big our entire solar system fits inside its shadow. Both are real. And the bigger one is, in some ways, less deadly at the edge. We talk about black holes like they're all the same. Dark, dangerous, weird, but they come in sizes that break your intuition. We're going to climb that ladder from city-sized to solar system-sized through three people whose lives orbit these things. Dr. Lena Ortiz grew up under the wrong sky. In Santiago, Chile, city lights washed the stars into a gray smear. On weekends, her father drove her north into the Atacama Desert. Out there, the Milky Way wasn't a smudge, it was a river. So bright, she remembers, it felt like it should cast shadows. She watched meteors cut through that river and asked herself, what's hiding behind all that light? Now Lena is an observational astronomer. Her specialty, X-ray binaries and stellar mass black holes. She doesn't see the black holes. She sees their victims, a bright blue star whipping around an invisible point, a hot, glowing disk of gas spiraling into nothing. When a massive star, maybe 20 or 30 times the mass of the sun, runs out of fuel, its core collapses. If that core is heavy enough, not even nuclear forces can hold it up. It collapses past the neutron star stage into a black hole. What's left is a region of space-time where escape velocity is faster than light. The boundary of that region is the event horizon. Stellar black holes usually have between about 3 and 165 times the sun's mass from single-star evolution. Mergers can make heavier ones. The radius of a simple, non-spinning black hole's horizon is about 3 kilometers per solar mass. So a 10 solar mass black hole has a horizon 30 kilometers across. 30 kilometers, 10 suns worth of mass inside something smaller than a major city. Lena's students always ask, how big is that really? Imagine, she says, you took the sun and shrank it until it fit inside your commute. That's a baby black hole, and that baby bends light around it like glass. She finds them by watching visible stars orbit invisible companions. If the star's wobble says it's bound to something compact and massive that emits almost no light, that's her ghost. If hot gas from the companion star spirals in, it heats and shines in X-rays, marking the black hole's presence. Every detection is a tiny triumph, a new point at the bottom of the size ladder. Lena still gets goosebumps each time. It's like discovering a hole in reality, she tells a colleague after confirming one, something that shouldn't exist but does. I sometimes wake up at night thinking about what it would be like to fall into one. What would you see in those final moments? But these are just the babies. Somewhere above them, the monsters get bigger. Much bigger. Dr. Arun Patel doesn't watch black holes. He listens to them. He grew up in Mumbai in a house where someone was always playing music, old Bollywood songs, metal band rehearsals. He loved feeling bass make the windows hum. In college, he heard a sound that wasn't supposed to exist. 2 black holes colliding, compressed into audio. It was a soft, rising whoop. What you're hearing, his professor said, is space-time itself ringing. Arun's father was deaf. He taught me that feeling vibrations was another way of hearing, Arun says later. When I realized LIGO lets us feel the vibrations of space-time itself, I knew this was how I wanted to listen to the universe. Now he works with gravitational wave detectors like LIGO and Virgo, long vacuum-sealed tunnels with lasers bouncing between mirrors. When a gravitational wave passes, it stretches one arm and squeezes the other by less than 1,000th the width of a proton. That tiny change alters how the laser beams interfere. Gravitational waves are ripples in space-time produced when massive objects accelerate, like 2 black holes orbiting and merging. They travel at light speed and carry energy and information about their source. The first big detection, GW150914, came from 2 black holes of about 36 and 29 solar masses. They merged into one of about 62 solar masses. Roughly 3 solar masses worth of energy went out as gravitational waves in under half a second. For that instant, the merger outshone every star in the observable universe, if you measure power in gravitational radiation. From the pitch and shape of each chirp, Arun can reconstruct the masses. Most signals are from black holes 10-50 times the Sun, but some outliers stand out. Mergers that leave behind black holes around 80, 100, even 142 solar masses. Too big to form easily from single stars. Too small to be the central monsters in galaxies. These are candidates for intermediate mass black holes, the missing middle. Over lunch, Aaron explains it to a colleague. It's like finding lots of kids and lots of adults, but almost no teenagers. Either teenagers are really good at hiding, or something weird happens while they grow up. He knows Lena's baby black holes. He knows, from the literature, about the giants in galaxy cores. But between 100 and 100,000 solar masses, almost nothing. A gap in the size ladder. Are intermediate black holes truly rare, or just very, very quiet? While Arun listens for those elusive teenagers, Professor Ada Mensa lives at the top of the ladder. She grew up in Accra, Ghana. When her father died suddenly, she coped by disappearing into books on relativity. Black holes were comforting, she says. If something can bend time, I could imagine a place where the worst moments haven't happened yet. She knows that isn't how physics works, but it's why she stayed. Now she uses simulations and observations to map the biggest black holes in the universe. At the center of our Milky Way sits Sagittarius A, about 4 million times the mass of the Sun. We know this because we can literally watch stars, S-stars, loop around an invisible point in a few decades. Sagittarius A's event horizon is about 12 million kilometers across. Huge, but still well inside Mercury's orbit. In other galaxies, Ada wrestles with true giants, black holes with 100 million solar masses, a billion suns, and a few extreme candidates at tens of billions. The black hole in the quasar TON 618 is estimated at 66 billion solar masses. Its event horizon would be roughly 200 billion kilometers wide, more than 30 times the distance from the Sun to Pluto. Everything we call the solar system would fit inside that shadow. Ada runs simulation after simulation. Something bothers her. We see quasars powered by billion solar mass black holes less than a billion years after the Big Bang. A black hole feeding steadily at the Eddington limit, where radiation pressure just balances gravity, roughly doubles its mass every 45 million years. Going from a 100 solar mass seed to a billion solar masses that way takes about 800 million years. Some early quasars seem to hit that mass with almost no time to spare. Either the universe is stretching the rules, Ada jokes darkly, or we don't know all the rules yet. Maybe the first seeds were already heavy, 10,000 or 100,000 solar masses formed by direct collapse of massive gas clouds. Maybe they sometimes ate above the Eddington limit. Or maybe we're missing whole chapters about how black holes are born. That's the second big twist. Some black holes might be born big. Skipping the baby phase. Let's step back and line them up. At the bottom, Lena's ghosts, stellar black holes, 365 solar masses from single stars, up to 150 from mergers. Event horizons only a few to a few hundred kilometers across, city-sized. Above them, Arun's missing teens, intermediate mass black holes, around 100,000 solar masses, horizons from hundreds to hundreds of thousands of kilometers, from smaller than Earth to bigger than the Sun. Then Ada's beasts, supermassive black holes, 100,000 to 10 billion solar masses, horizons millions to billions of kilometers wide, from inside Mercury's orbit to far beyond Pluto's, and at the insane upper end, ultramassive black holes, more than 10 billion solar masses, horizons tens to hundreds of billions of kilometers across, big enough to swallow entire star systems. But mass doesn't just change size, it changes how it feels to approach. In a strong gravitational field, what kills you is the tidal force, the difference in gravity between your head and your feet. For a small stellar black hole, the event horizon lies so close to the center that this gradient is extreme. You'd be stretched, spaghettified, before you ever reach the horizon. For an ultramassive black hole, the event horizon is millions or billions of kilometers from the center. Over the 2 meters of your body, gravity hardly changes at all. Tidal forces at a given distance scale roughly like mass divided by radius cubed. For big black holes, the radius at the horizon is so large that the gradient over your height is tiny. Paradoxically, the bigger the black hole, the more gentle its edge feels. You could, in principle, fall through the horizon of an ultramassive black hole without feeling anything special, at least initially. No flash, no tearing, just quietly crossing a line in spacetime that you can never cross back. Lena used to think of black holes as drains. Aaron thinks of them as bells. Ada's simulations reveal they're also thermostats. When gas falls into a supermassive black hole, it forms a blazing accretion disk. Magnetic fields can launch enormous jets of plasma at nearly light speed. Those jets and winds slam into the galaxy's gas, heating it, stirring it, sometimes blowing it out of the galaxy entirely. If lots of gas stays cold, a galaxy goes into starburst mode. New stars everywhere, supernovae everywhere, lots of fuel tumbling inward. The black hole feeds and brightens. Its feedback, radiation and jets, heats and expels gas. Star formation slows or stops. The galaxy quenches, turning from a blue star-forming spiral to a red, quiet elliptical. Astronomers see a tight relationship. The mass of the central black hole correlates with how fast stars move in the galaxy's bulge, the M-sigma relation. Bigger black hole, heavier, dynamically hotter bulge. The giant in the middle and the galaxy around it grow together. Black holes aren't just passengers, they're co-architects. They help decide how many stars and how many potential habitable worlds a galaxy gets. For decades, black holes were beautiful math and indirect clues. Then, in 2019, the Event Horizon Telescope gave us an image we'd been chasing for a century. M87 Keys, a supermassive black hole about 6.5 billion times the Sun's mass, 55 million light-years away. We didn't see the black hole itself. We saw its shadow, a dark circle, larger than the event horizon, where light is captured or bent away, silhouetted against glowing hot gas. The shape and size matched Einstein's predictions almost perfectly. Lena watched the press conference in the observatory cafeteria. Someone taped a grainy printout over the coffee machine. For a few minutes, nobody spoke. They just stared. Aaron sat alone in the LIGO control room, playing a simulated gravitational wave signal from a black hole that massive. So that's what you look like when you ring, he thought. Ada printed a high-res copy and pinned it above her desk, next to a photo of her. Father. It's real, she whispered. Not just equations. We took a picture of space-time refusing to let light go. From Lena's city-sized stellar remnants, to Aaron's colliding intermediates, to Ada's ultramassive engines sculpting entire galaxies. Black holes cover a size range that's almost impossible to imagine. Yet at first approximation, they're simple. A non-spinning, uncharged black hole is fully described by one number, its mass. Add spin and charge and you get 2 more. 3 numbers to describe something that can erase worlds. A 10 solar mass black hole and a 10 billion solar mass black hole follow the same equations. Only the scale, and what that scale means, changes. The small ones tear apart nearby stars. The big ones decide how bright a galaxy is allowed to be. Without them, galaxies might look very different. Maybe too chaotic, maybe too short-lived, maybe too quiet. So when you hear black hole, don't just think cosmic destruction. Think scaffolding, feedback, regulator, and yes, the ultimate size comparison flex in the universe. From stellar to ultramassive, black holes are not just the monsters of the cosmos. They're some of its most important tools, and they're still hiding secrets at every rung of the ladder.